I chose problem 1 from 1999, not just because it's a very old problem, but also because this illustrates the greatest point for the E&M problems. If you know things like Gauss's law and you remember certain things about conductors, capacitors, that sort of thing, the problems actually become very, very easy and there isn't a whole lot of math involved. So I'm going to use a couple tricks on this problem in order to make my life easy. Okay, so we've got a sphere, it's got some charge on it. We know the potential of the sphere is negative 2,000. In part A, they say determine the charge Q naught on the sphere. We can treat it as a point charge, so we recall that the potential for a point charge is Q over 4 pi epsilon naught R. They gave us the 2,000 minus 2,000 is equal to Q over 4 pi epsilon naught. We put in the radius for that sphere as 0.2 because we're going to treat it like a point charge. And we get that the charge is equal to negative 4.4 times 10 to the minus 8 coulombs. That minus sign is important. You actually lose a point if you do not include the correct sign on the charge. The rest of the problems basically deal with magnitude, so you got to be careful for when they're asking you for it. Okay, now we're going to create a spherical capacitor here, okay? I don't actually think the language is very good on this one, except for the part where it says that it's forming a spherical capacitor. I actually got very confused when it said a wire is connected from the outer surface to the ground and then removed, okay? By making it a spherical capacitor, you know that the two plates have to have the same amount of charge. So that means that the inner sphere has this charge, negative 4.4 times 10 to the minus 8 coulombs. And now the outer shell has to have the opposite charge. Remember, for a capacitor, one plate has to be kept at one charge, the other one has to be the opposite charge. So the exact same thing's going to happen here. Okay? Determine the magnitude of the electric field in the following regions as a function of distance r from the center. Okay, in the first region, you're inside of a conductor. You guys should remember that there is no electric field inside of a conductor, so in the first region, the electric field is going to be 0. There's a point right there. In the second region, we're now in between the spherical, the sphere and then the spherical shell, okay? So that means that the electric field should fall off as a normal electric field. Think about the charge right at the center. Q over 4 pi epsilon naught r squared, okay? We know that the charge, since they're just asking for magnitude of the electric field, we don't have to worry about the minus sign. That's 4.4 times 10 to the negative 8th. And then the r squared is going to be down here. As you get further away from that center sphere, the electric field is going to die off. Okay? Not really that complicated. Next region, you're once again into a conductor, so the electric field has to be 0. Then you move beyond the conductor, so now we're outside of the whole capacitor. This is where you have to take a second to really remember. If you think about Gauss's law, Q enclosed over epsilon naught for figuring out the electric field, the total charge is now 0 because you have that negative charge at the center of the conductor and then you have the opposite charge on the outside. So the Q enclosed, or those two charges added together, Q enclosed is now 0, so the electric field outside the capacitor must also be 0. I got that wrong initially. I wanted to start trying to calculate that. I forgot about the nature of capacitors. One plate has to be at one charge, the other plate has to be at directly the opposite charge. Determine the magnitude of the potential difference between the sphere and the conducting shell. Very straightforward. Potential difference would be the potential difference at the radius B minus the potential difference at the radius A. Very straightforward calculation. You should get 1,000 volts right there. That's very, very easy. Okay? Lastly, determine the capacitance of the spherical capacitor. Get into the rhythm of this. It's exactly like the mechanics exam where you sometimes use previous answers in order to answer the new answer. Don't leave it blank. Write something down. If you couldn't figure out this voltage right here, that's totally fine. If you put down that you know that charge is equal to voltage times capacitance, you would get a point right here. You might even get 2 points, depending on how many points each problem is worth. So definitely write something down. We know the charge. We know the voltage, the potential difference between the plates. I just found that. We can calculate the capacitance very straightforward. Okay? But remember, using things like Gauss's law, Q enclosed over epsilon naught, and then also remembering the nature of conductors, no electric field inside, and capacitors, one plate at one charge, the other one at the opposite charge, we were able to kind of hand wave a lot of work here. There wasn't a whole lot of math that we had to worry about. That is going to be typical for E&M problems.